Hello, Precalculus student. This video is for chapter 1.4, still on composition of function, but we are looking at the reverse of it, which is decomposition of a function. So sometimes when we look at a function, we see that it is complicated, is not directly a sum or products of two kid function or parent function. So it seems like it has it's formed by a composition or formed by two functions in sequences. So we like to decompose these kind of function into the form of an inside function and an outside function. So if I write FOG of x, you know that this is a composition. That means I put x into G first, and then I put the G of x into F. So you can see G of x is the inside function because it is the input into F of x, and F is the outside function. So that's exactly what we want to do when we do function decomposition. For example, h of x equal to square root of 5 minus x squared. We can look at the inside as 5 minus x squared. So that means when I start off with x, I do 5 minus x squared first. So I can say this is the inside, right? And the inside would be the g of x. So I would write g of x is equal to 5 minus x squared. And after that, I've put it into a function that's do the square root. And then f of x is not square root of the whole thing, but just square root of whatever that is being input. In this case, my input is g of x, so that's why I have square root of 5 minus x squared. So if we do that, then h of x is actually f of g of x, or f of g of x. So in all cases, so this would be our answer. We want to know the inside function and define the outside, which is the final product that would result in the final products of the original h of x. So we call this function decomposition. It is a skill that you need to know in a calculus. So in a certain operation of calculus, you need to identify inside and outside function, be able to split the function into layers of functions. So let's say h of x is now x minus 4 to the 6th power. So obviously we would recognize this as the inside function. We would say, oh, g of x is x minus 4. And then I put x minus 4 into a function that raise it to 6th power. So my f of x, which is outside, is x to the 6th. So that h of x is FOG of x. So these are the two answers. G of x is inside. F of x is x to the 6th is the outside. What about this? So I see h of x equal to 1 over square root of 4 minus x. Now, there's different way of doing this. So one way is looking at the inside as 4 minus x, right? You can just say the beginning, I do 4 minus x. And then the outside would, f of x. f of x outside would just take this, square root it, and then do 1 over, right? So that's one way. The other way is you can see g of x as square root of 4 minus x. Square root the whole thing, and then you give it to the outside function f of x is just doing the 1 over it. So both are okay. So that's function decomposition, and that's the end of 1.4. So we're going to do 1.5, which is transformation of function. Transformation of function, we lay how when you make some changes to the function input as well as the function output, you can use this relationship to graph a function. Okay, so if I have a function f of x and I horizontally shift f of x by h, the new function is to the left. The new function is f of x plus h. If I shift the whole thing To the right, the whole function, the new function is f of x minus h, and every single x will increase by h to the right. So notice plus h will to the left, minus x to the right. And if I take my f of x and I add a number outside, notice when you do horizontally, it is inside. Do vertically is outside, adding or subtracting a number. So this can be illustrated by actually going into decimal. So for example, I just pick a function y equal to x squared. Okay, so if I do y equal to, but instead of x squared, I say x plus 1. That means I replace x by, in original is x, now is x plus 1. So the blue one, actually, when I add 1, shift to the left. Right? If I say y equal to x minus 3 to the 3, to the square. So it's exactly the same graph, but I move everything to the right. So add a number is shift to the left. Minus a number inside is to the right. Okay, so let's do this. And then what about if I just do x squared and then I plus 8? Oh, no, that's too much. And you will see that the purple one is just adding 1 outside. It's the whole graph move up 1. And if I do x squared minus 3, it move down. Okay, so adding number outside or inside corresponds to, we call it a transformation of shifting the function. The original function is x squared, but I transform it. Okay, so these are the way we write it, but you can recognize it by using a real example of a function. So if someone write a function f of x and then they write another function graph of f of x minus 1 minus 2, what would this what transformation would it would occur? So remember, 9 minus 1 is horizontal, so this would be horizontal to the right. If you minus 1 is to the right, just like when we have it here, minus 3. Oh, you can see that the green graph moved to the right. Okay, minus 2 outside is down 2. So whatever function f you have, if you graph another one that goes like this, it would have a transformation with horizontal right 1 and then down 2. What about x plus 4 inside? So this is a horizontal shift, I should say shift. So the shape of the graph, it looks exactly the same. And if I do plus, it will be left 4 plus 3 is up 3. So that's transformation, left and right, up and down, keeping the whole shape of the function. Another example would be give you a, parent function and give you a transformation. Can you write the equation? So the equation would become y equal to, if I shift down 3, it would be minus 3. Right 1 would mean the inside with minus 1, right? So this would be a transformation that corresponds to shift down 3 and shift right 1. Another one. So if I have a parent function of a square root x and I want to write another function or a formula that will involve shifting square root x up 3, so I have to add 3, but left 2. So left and right is inside. For left, it is plus 2. Up 3 is up 3 outside. Inside, left and right, outside, up and down. The third example would be someone graph a function and you are to use the transformation meaning to discover what this information is. So this looks like an x squared toolkit function, parent function, but it's down 20, right? So it's down 20. So you would say it's x squared minus 20. This looks like a absolute value function, but it shifts to the right by 3. So inside you add you minus 3, but it's down 2, minus 2. This one seems to be a square root function that have shifts to the left by 3. So we add 3. And up and down is down 1. So by looking at, understanding how what have changed to the original two-kit function, you can actually write a formula. Now, this is the other way around. If someone write a formula, and this is actually the ultimate goal, if someone write a formula that is very close to a two-kit function, so you would say, what is the parent function or the two-kit function? Two-kit function is y equal to absolute x. But the transformation is, describe the transformation that happened. That is manifested by the equation. So inside have add 1. That means left 1 and down 3. So you would imagine a original square root function like this, right? And you would graph it, not by graphing points, but shifting it left 1 and then down 2. So that would be the new function for this graph. If I want to sketch a graph of 1 over x plus 1 minus 3, so I would say the parent is 1 over x, which is kind of like that, right? Now, what kind of transformation do I have? I have plus 1 again, also left 1. Oh, it is exactly the same, and then down 3. Oh, this is down, not down 2, it's down 3. Down 3. I must have just copy it. So I would say the whole branches with left 1. So this is the original x-axis and y-axis, but I would do a new dots here and down 3, right? So the graph would be like that, as if the whole thing moved here. Okay, so that's how you graph a function given a formula. So using transformation technique. So the next video we'll talk about another set of transformation that is not just shift left, right, up, down, but reflection, stretch, and compression.